Welcome everyone to day 23 of the Womanium Global Quantum and AI program. And we are delighted to have Jin-Sung Kim from NVIDIA with us. Jin-Sung Kim is the Developer Relations Manager for Quantum Computing at NVIDIA, based out of San Francisco. And in his role, he manages technical collaborations and the rapidly growing NVIDIA quantum ecosystem. Before NVIDIA, he was research staff member at IBM Quantum. And before that, he completed a PhD at Princeton University in electrical engineering and materials science. Jin-Sung, we are very excited to have you here and very excited for your talk. Please take it away on the generative quantum Eigensolver.
Great. Thanks for that great introduction, and thanks for having me on this fantastic series. So my name is Jin-Sung Kim. I'm from the quantum team at NVIDIA, and I'll be talking to you today about some recent work that we put out on an archive called the Generative Quantum Eigensolver. So for today's talk, I'll briefly give some context and background about NVIDIA as a company and what we're doing within the quantum computing space. I'll talk about CUDA-Q, our platform for hybrid quantum classical computing. And then we'll dig into the details of the generative quantum eigensolver. So NVIDIA has a long history of supporting accelerated computing. If you know anything about the history of NVIDIA, back around 2006, we released a framework called CUDA, which enabled folks to start programming GPUs alongside CPUs. And this was really instrumental for kicking off deep learning and machine learning and modern AI. So this was really the spark point for enabling all of these very, very interesting and powerful technologies. And so what we see today is a lot of parallels between quantum computing today and what deep learning and generative AI were 10, 15, 20 years ago, where there's a lot of potential that we saw within the field. And our strategy at the time was to enable the largest amount of developers with the best scientific tools to do their life's greatest work. So after we released CUDA, this really kicked off a real revolution within deep learning. So this enabled folks to actually show how the first deep neural networks could actually be used for perception. So this led to what's now famously known as AlexNet, and this is one of the best image recognition programs that was released at the time. And this led to the advent of generative AI. And you can see in the small photo here, our CEO, Jensen Huang, delivering one of the first DGX systems to OpenAI. And of course, this leads to the advent of ChatGPT and all of the AI tools that you know and love today. So what we see within quantum computing is a very similar trajectory as deep learning and machine learning and generative AI about 15 years ago. So our strategy for quantum computing is very similar to the strategy of deep learning and machine learning. So let me talk a little bit about what our quantum platform does today. So CUDA-Q is a unified platform for hybrid quantum classical computing. The future of all useful computing will be some sort of hybrid model. So the CPU will be doing something that's very good at, the GPU will be doing something that's specialized for, and the quantum processor will be doing something that's specialized for. And so having a unified and very performant and flexible programming model and platform to enable all of this will be instrumental for actually achieving something useful with a hybrid quantum classical supercomputer. So within CUDA-Q, our various libraries for applications includes the programming model for abstracting away the various components of a quantum accelerated supercomputer. There's very powerful simulation libraries on the back end for doing large scale and very performant quantum circuit simulation. And we also include the tools for HPC and quantum integration, enabling a very tight integration between classical and quantum resources. On top of this, we're also developing tools for AI for quantum. So instead of asking, what can quantum do for AI in the future? This is also a very important question. We're thinking about what can AI do for quantum today? And at the systems level, what we've designed is a system called DGX Quantum, which tightly integrates at the systems level a quantum processor and the control hardware of a quantum processor and a GPU system, enabling a truly tight systems level integration. So all of this put together and wrapped up enables something that we like to call a quantum accelerated supercomputer. So a big part of our strategy is to enable the entire quantum ecosystem. So you'll see in our ecosystem slide here that we work with a wide variety of quantum hardware builders who are integrating CUDA quantum or using our simulation tools for their hardware. We've integrated into a wide variety of quantum simulation frameworks. We've been working with many different systems builders and integrators. We're working with a lot of different quantum software and systems providers who are building applications and software on top of the tools that we provide, as well as we're working with various research centers around the world who have deployed CUDA quantum and our other tools on their supercomputers. So let me talk a little bit about some of the performance of CUDA quantum. What I'm showing here on the left is just a simple GPU speedup over CPU for a typical quantum workload. I believe in this example, it's a quantum neural network example that we're running on 4 A100 GPUs and comparing the runtime to running the same workload on a single CPU. And you can see that there's a really massive performance benefit for running your workload on a GPU over a CPU. So we're seeing, upwards of almost 2,500x times faster performance running on 4 A100 GPUs compared to a single CPU. So really significant performance benefits for running your workloads on the GPU over CPU. And of course, we're integrating with a wide variety of different quantum hardware providers to enable folks to not only simulate their systems on their either local laptop or GPU, but actually start to run quantum applications on any one of our partner backends. So let's talk a little bit about generative AI for quantum computing. I'm sure many of you have used generative AI tools or have heard of them. And recently, there's been a huge explosion of workloads in the past few years using generative AI for things like image and video creation, along with code and text generation, where AI models have been trained to generate useful tasks or content for the user. So this leads to a natural question within quantum computing. In what ways can generative AI accelerate quantum computing research? So this is the question that led us to the development of the generative quantum Eigensolver. I want to note that this work was done in collaboration with the University of Toronto and St. Jude Children's Research Hospital, led by Alon Asperu-Guzik. And I especially want to acknowledge Koei Nakaji from University of Toronto and Pooja Rao from NVIDIA, who led the majority of the technical work presented here. So let me give a little bit of background on the generative quantum Eigensolver. I'm sure most folks have heard of the variational quantum Eigensolver, or the VQE. The VQE is one of the most highly cited and used algorithms for quantum chemistry in quantum computing, especially on near-term quantum processors. And I want to point out that Alon Asperu-Guzik was actually one of the inventors of the variational quantum Eigensolver back in 2014. So we think of the GQE, the generative quantum Eigensolver, as kind of an orthogonal method to the variational quantum Eigensolver. So just as a reminder, the way the VQE works is you have some sort of parameterized onsets or guess of how the electrons in your molecule are arranged. And you feed this guess into a quantum processor, which, while varying some of the parameters in your onsets, and the quantum processor gives you back an estimate of the energy of that configuration. And then you vary your parameters and you do an optimization loop to figure out what are the best parameters that give you back the lowest energy of the system. And you take that to be the ground state energy and configuration of your system. So the VQE is really nice in that you can run it on a near-term quantum processor, and it also kind of nominally guarantees an upper bound on your ground state energy so that you can be relatively confident that the energy the variational quantum Eigensolver gives you won't go below the true ground state. And this technique works pretty well for small molecules with a small number of parameters. But once you go above a certain system size, you start to run into some issues with the VQE. One of the biggest issues here is the so-called barren plateau problem. So this is where your system is trying to find the global minimum, of the energy, but you get stuck in some sort of local minimum, and you're kind of tricked into thinking that this is your true global minimum. And there's really an outstanding issue with the VQE. So with the generative quantum eigensolver, we attempt to address some of the shortcomings of the VQE by using a classical generative model and to leverage the training capabilities and scalability of a classical model to do so. So what we do with the GQE, shown in this lower diagram here, is train a classical GPT model to generate circuits which yield interesting properties of a given system. So in this specific work, we use it to generate circuits that give us a good approximation of the ground state energy of a molecule in question. And the parameters within the GQE are held within the weights of a classical neural network, which can be trained using classical backpropagation with the appropriately provided cost function, which is the energy of the molecule here. And by training the model this way, we can generate appropriate data sets either through simulation or by sending these circuits to an actual quantum processor, which I'll talk about later. We can actually train the GPT model to give us circuits and then data sets, which we can do pre-training on other systems of interest without needing an actual quantum device in the loop, and just use the infrastructure of the GPT model to do the training. So I'll talk more about that very interesting property of this work in a couple of slides. Okay, so let's talk about how the GPT model works for the generative quantum eigensolver now. So at a very high level, you can think of quantum gates as analogous to words in a vocabulary. And if we're thinking about large language models in the context of text, you can similarly draw parallels from quantum gates to words and quantum circuits to sentences. And so in the same way that a GPT model can generate meaningful and coherent text using a large language model, we can generate quantum circuits that yield meaning, or in this case, the energy of a molecule in question. So the way that this works is we have our transformer model. We define an operator pool of chart-arrays polystrings using the UCCSD ansatz. And for a given molecule, we can use the molecular Hamiltonian in a given basis as our cost function. So for this work, we're using a few different time steps for our Trotter decomposition. And our initial state is the typical Hartree-Fock state. And we use CUDA-Q to do the quantum circuit execution and compute the energy of the state. We then do the training using kind of standard backpropagation methods, and we eventually the training settles on a sequence of gates that gives us a good approximation of the ground state energy. So what does this look like in practice for a couple of different molecules? So we looked at a couple of different molecules and trained the model on H2, lithium hydride, beryllium hydride, and N2. And we're varying the interatomic distances and computing the ground state for each in 3 different ways. So for the first way, this is just the Hartree-Fock ansatz. That's the very top curve. The solid line is the exact diagonalization. And then the green data points are the energies we derive using the GPT-QE. So you can see that with the generative quantum eigensolver, we get results that are very close to the ground state energy. And the main point here is that we can use classical AI techniques to get a very good ansatz for the ground state energy of a molecule, which can then be further refined through a variety of different methods. So one thing that we're also really excited about are kind of the future directions of this work. We really think we're just starting to scratch the surface of what's possible with generative AI methods for quantum computing. I do want to mention that this work was executed on Perlmutter, which is a very powerful GPU supercomputer at NERSC with over 6,000 NVIDIA A100 GPUs. And this was done through the QIS at Perlmutter program, which is a fantastic program for enabling quantum computing research on a GPU supercomputer, which has an open call for proposals every year. So if you have some sort of interesting quantum research problem that could use one of the most powerful GPU supercomputers in the world, you should definitely look into this program. Okay, so let's talk about a really interesting byproduct of some of the initial training runs that we performed. So when we train a GPT model for this work, we generate a circuit, which is a sequence of gates, and we execute the circuit on the simulator and compute an energy expectation. This process is repeated many times in order to train the model to yield the right sequence of gates to yield a good approximation of the ground state energy. And one of the most expensive parts of this process is computing the energy expectation, or the cost function, which either requires a powerful simulator or access to a high-quality quantum processor. So what we want to do is minimize the number of times that we have to do this process. So luckily, we only need to do this once per circuit. And once we have a sequence of gates and their associated energy expectation, we can just literally save these into a database. And now we have a very good data set for training other similar models. So let's talk about 3 ways these data sets can be leveraged for other interesting use cases. The first is the model-to-model transfer. So what we can do is use the same data set that we just generated to test another GPT model. So for example, if we train our first model on a given molecule using a model we'll call GPT-A, and generate a data set in that process. And suppose GPT-A doesn't give us a satisfactory model, and we want to test another GPT model that we'll call GPT-B. So maybe this new model has a different network architecture, or has a different number of attention layers, or any other details in the model that we want to change or explore. We can use the exact same data set to pre-train our second GPT model, GPT-B, in order to kind of warm start the training process and see if GPT-B performs better than our original model. The second is configuration to configuration transfer. So in this case, we're going to use the same model and the same molecule, but now just change a parameter of the Hamiltonian. So for example, in the case of ground state energy calculation, we can just adjust the interatomic distance and use the same pre-training scheme to speed up the training of the model, or a slightly different interatomic distance. And this, the effect of this really speeds up the training process for this new interatomic distance. The final way, and most trickiest, but also most exciting, is the molecule-to-molecule transfer. So we propose utilizing the data set generated from the training of one molecule to pre-train another. So this is a very exciting prospect because of the possibility of finding the ground state energy of an unknown molecule given a data set of a known molecule. So this is still emerging research and would require extensions to the original model, but one can think of cleverer ways of representing the Hamiltonian, which are more transferable to another molecule. But that is that's outside of the scope of this talk. Okay, so let's look at a little bit about how the GPT-QE model is implemented with a little bit of pseudocode. So really, there's just a couple of steps that are involved here. First, you set up the transformer model, number of layers, learning rate, etc. This is done in setup transformer. We set up the operator pool. So we have a bunch of operators that are taken from the UCC SD operators. These are just a bunch of different polystrings, and we set a couple of different evolution times for each one of these. So we're actually time evolving each one of these for a couple of different time steps here for a Trotter evolution. So for example, what the operator pool looks like for the hydrogen ground state search, I've just listed a couple of operators and their associated times here. So each training epoch does the following, and each circuit sample does the following. The transformer picks a sequence of specified number of operators from this pool to construct a circuit. We construct the circuit from each one of these sequences by trotterizing the polywords over the specified times, and then we evaluate the circuit to evaluate its energy. And then this gets backpropagated and adjusted so that the network weights are adjusted. Okay, so I want to also talk about the training performance and how much of a benefit being able to use multiple GPUs for this process is. So I mentioned before that we can use CUDA-Q with the GQE to allow multi-node and multi-GPU parallelization. And I just want to show a couple of the scaling benefits of actually using CUDA-Q and multiple GPUs for this process. So just to give you a flavor of how long it takes to train one of these models, for GPT-4, I believe that was trained, using tens of thousands of GPUs over the course of several months, continuous training. For this work, it's a bit of a smaller model, but it still is non-trivial amount of training work that has to be done. So for example, we did a 30-qubit run with 50 samples and 50 epochs on a single H100 GPU, and this trained in about 173 hours. So not a non-significant amount of time, but what we can do is actually parallelize this across multiple GPUs. And when we do this, the performance is nearly linear. And so when we move to about 48 GPUs, we can do the same training in about 3.5 hours. So really, really significant performance benefits that are possible here. I also want to do one quick kind of baseline speedup comparison in showing how long it takes running on a CPU to GPU on an 18-qubit problem. So what we're seeing here is a nearly 40x speedup running on a single GPU over a single CPU. And then 320x faster, moving to 8 H100 GPUs over a single CPU. And I want to mention that this was done on a smaller system, an 18-qubit CO2 run, and the CPU actually did not succeed for the 30-qubit simulation. Okay, so I mentioned that this is really just the tip of the iceberg for generative AI models for quantum computing. And we think this is really just one of the first examples of understanding how GPT models can enable quantum accelerated supercomputing. And there's a bunch of different applications that we think this can be used for, not just quantum chemistry, but definitely material science and other environmental applications. And definitely new applications within other algorithms like QAOA. Other interesting things that people are exploring are so-called quantum geometric machine learning. And I also want to point out that this code is going to be made publicly available alongside the CUDA-Q 0.8 release, which should be out in the next couple of months. I do also want to point out that there has been an explosion of research within AI for quantum. So this is not just in the generating quantum circuits, but there's a lot of work that's being done in the calibration and control and readout of various quantum hardware. So there's some really great works that I'm pointing out here where folks are using various flavors of machine learning to improve the calibration and the performance of quantum hardware today. As well as circuit optimization using various machine learning methods, as well as for error correction. So these are all critical things that are necessary for enabling a useful quantum computer of the future that are being accelerated by AI today. So how do you get involved? The easiest thing that you can do is download CUDA-Q onto your local machine. You can run it on a CPU on your laptop. You can run it on a GPU if you have one available to you. There's also various programs around the world that enable you to get access to GPU time on supercomputers. The GQE code will be made available soon. I think I forgot to mention that CUDA-Q is also open source. So definitely contribute to the open source community, contribute to open source, open issues on the GitHub. And we want to know how AI can accelerate your quantum computing research. So that brings me to the end of my talk, and thank you for your time.